1 times n minus 2 times n minus 3, dot, 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 all the way out to 1. I could square each one, yes. There's a reason I didn't, though. Let's look at a pattern here. See this right here, that's 1, right? Agreed? Mm-hmm. Okay, and then what else can I kill off here? I know that this right here is smaller than 1, isn't it? This right here, smaller than 1, smaller than 1, all the way till I get to here. Yeah? So if you want, you could say that each of these is smaller than 1, smaller than 1, smaller than 1, smaller than 1, all the way to here, smaller than 1. Well, would it be the same answer squared? Is that what you're saying?
Like 1 squared is still 1, right? If you still get 1.
N minus, here's your question. Is n minus 1 squared over n always smaller than 1? Is that true? Is this always smaller than 1? Let me give you an example. Let n be 3. Or let's let n be 4, okay? Let n be 4. What do you get? If n is 4, you get 3 squared over 4. Is that bigger? Is that smaller than 1? See? The squaring has a major impact on this. Now, if n is 2, it does work, but once you get to n is, what, 3? Will it work with 3? 3, 2 squared, 3. Yeah, so it's... No, because these are all squares. These powers aren't getting bigger and bigger and bigger, right? What's your feeling here? Say it again?
N factorial over n.
Where are you getting over n from?
You have that, last time you did it, it was all equal to 1 over n, but this time you still have an n factorial on top.
Yeah, this is an n factorial right here, right? We know that this by itself, right here, we know that that would go to 0, right? That part goes to 0. But what does this part go to? This goes to infinity, right? That's n factorial. So we have like a 0 times infinity. And yeah, I don't see it. I think this thing's going to be beyond the grasp of what we can do. So that's why I said when I put it up here, I was like, I'm going to put something up here because I'm just curious, but it's not something we can squeeze. I mean, the most we can say is that this is less than or equal to n factorial. But that goes to infinity. And there's no way I can squeeze something in between infinity, right? I mean, yes, this goes to something between 0 and infinity. All right, great. That doesn't help, right? It needs to squeeze to the two same places. All right. Maybe I'll work on that on my own free time and see if I can come up with a good one to finish that out. All right. A theorem, another theorem. If the absolute value of a sub n goes to 0, then a sub n goes to 0. If you have a sequence in which its absolute value goes to 0, then the sequence without the absolute value must go to 0 also. So let's take a look at an example of this. A sub n equals -1 over n. No, -1 to the n over n. So you look at that and you say, okay, I've got this alternating happening, right? This theorem says, hey, look, if you've ever got alternating happening, take a look at the absolute value. So let's just look at what is the limit as n goes to infinity of the absolute value of -1 to the n over n. Now, what does taking the absolute value of this do for me? When you do this, right, it's going to be either 1 or -1. But when you take the absolute value, it's always going to spit out 1, isn't it? So this is the same as just doing limit as n goes to infinity of 1 over n, right? And what is that limit? 0. Therefore, the limit, or I'll just do it this way, -1 to the n over n converges to 0. So if we have a sequence that alternates, we can take the absolute value, and if the absolute value of the sequence goes to 0, then we can conclude that the original sequence goes to 0 also. It's a nice little theorem. It can speed things up later for us. So with that in mind, I'm going to put another one up here for you. How about just -1 to the n by itself? Absolute value. Let me try this theorem. Limit n goes to infinity, absolute value of -1 to the n. What is the absolute value of -1 to the n? What's the absolute value of this? This is either 1 or -1, right? Take the absolute value, you're just going to get 1. So this is the limit as n goes to infinity of 1. And what's the limit of a constant? It's just the constant, right? So your answer is 1. So can I say now, therefore, -1 to the n goes to 1. Can I say this? The absolute value of this sequence went to 1, so that means that the sequence itself goes to 1? No.
Doesn't it go to infinity?
Nope, this doesn't go to infinity. We've done this already. We said this diverges, right? Why is this theorem falling apart? Why am I not able to use it? Yeah, if the absolute value of the sequence goes to 0, then the original sequence goes to 0. This absolute value of the sequence goes to 1, which means you throw that theorem out the window because you can't use it. All right? So this would be an incorrect usage of that theorem. This is wrong. All right? So just be careful is what I'm getting at. The theorem does not apply. All right, we've got about 30 minutes. All right, we need some more definitions now. A sequence A sub n is called increasing if A sub n is less than A sub n plus 1 for all n. What does that mean? Yeah, so like if you look at the first term of the sequence, it's smaller than the second term, right? But the second term has to be smaller than the third, and the third has to be smaller than the fourth, and so on and so forth. So if we were to look at this graphically, whatever your first one is, your next one has to be slightly above it, right? And the next one of those has to be slightly above that one. And so what you get is an increasing sequence. Any sequence that follows this inequality for all n is an increasing sequence. Similarly, a decreasing sequence is one in which a sub n is bigger than a sub n plus 1 for all n. So that means the first one's bigger than the second one, which is bigger than the third one, which is bigger than the fourth one. And so that sequence would look something like this. Right? It's decreasing. So that's just definitions there. In either case, okay, either one of these, in a case in which your sequence is increasing or decreasing, these are called monotonic sequences. That's like if I say, hey, I've got this sequence and it's monotonic, all right? That means that it's either increasing or decreasing, one or the other. So this is not very specific, is it? If I tell you I have an increasing sequence, then that gives you a little more detail. But in either case, they're just called monotonic sequences. All right? Now, more definitions. A sequence A sub n is said to be bounded above if there exists a number, capital M, such that A sub n is less than capital M for all n. Bounded above. I'll draw you a picture. I'm going to draw you a sequence. Now, it's not going to be monotonic. It's just going to be some sequence. So I start here, start doing this and this and that and then that and that and that and that and whatever. There. And let's just say it keeps doing this sort of trend. I can say that this sequence is bounded above if I can find a capital M anywhere. Such that every term of my sequence, every single one of these, is smaller than this M. Then I can say it's bounded above. It's like a ceiling, right? It's like a roof. Everything lives underneath that roof. It is bounded above. Make sense? Similarly, we can say a sequence is said to be bounded below if there exists some number that's always smaller than the sequence, right? So I'm about to write all that again. But I'm actually going to do it with different notation, right? So I erase my picture. I'm going to write this the way a mathematician would write this, okay? This is more like in English. Let me write it the way a math person would do it. Sequence A sub n is bounded below if there exists a little m element of the real numbers such that A sub n is bigger than little m for all n. Okay, Okay, that's actually everything that's written on the left in notation. All right, almost word for word. Sequence A sub n is bounded below instead of above if there exists is this right here. That's the symbol we use for there exists. A little m instead of capital M. Now I said there exists a number m, right? Well, here I'm saying there exists an m that's an element of the real numbers. In other words, that's a number, right? Such that, we use st for such that, the inequality is flipped over, and this upside down capital A with the n here means for all n. Right? I'm just giving you kind of a perspective. Math people like to write this way because that's a lot less writing, isn't it? And it's symbolic, and these are called universal quantifiers, and there's a whole language to it, but that's the translation of that into math. Okay, this picture looks like this. Sequence, some m here, little m, that is a lower bound. None of those dots ever go lower than that little m. One more definition, and then one more theorem. A sequence A sub n is said to be bounded, and I'm going to ask for your opinions here. We're going to take a vote. A sequence A sub n is said to be bounded if, what do you think?
If they're between two numbers?
If it's between, you mean it's bounded above and below? Is that what you're thinking by what's about to happen? Mm-hmm. That sound right to everyone? If I tell you a sequence is bounded, to you does that mean above and below? Or just above or below? I guess my question is, do you think this means and, like to be bounded means you're bounded above and below? Or do you think it means bounded above or below? It's the and, all right? It's the and. So if a sequence is said to be bounded if it's bounded above and below. Now, it's kind of weird because when I said monotonic earlier, right, that was either increasing or decreasing, right? Monotonic meant increasing sequence or decreasing sequence. Here, when we say bounded, that doesn't mean bounded above or bounded below. It means bounded above and bounded below, both. All right. So being a bounded sequence is a pretty strong condition, isn't it? It means you have an upper bound and a lower bound for your sequence. And now we come to the theorem, last theorem, the bounded monotonic sequence theorem. And it's pretty straightforward. Very simple theorem. Every bounded monotonic sequence, what? What do you think?
Not up or down, just like straight scattered.
So it doesn't scatter around?
It does, but like straight, not like this one way. How to explain what I'm saying?
Try and come up with the conclusion of this actual theorem by just drawing a picture. You have a sequence, right? It's bounded, which means it has an upper bound and a lower bound, right? It's bounded above and